There it is.
Looks like we're there.
That's all.
Yeah, hopefully we're wonderful. Last module of the day, module 15, and this is just the basic 101 for surface water treatment production. So we're looking at and we're going to describe how surface water is made, what type of treatment processes we're going to go through to get it to that product where it's usable. We're going to look at major regulations that govern surface water. We'll describe the treatment process as well as treatment rules. All right, what are the sources of surface water? We have rivers, we have natural lakes, we have man-made lakes. And as you can see, I went to actually look into Delaware's rivers and lakes that are out there and came up with this little map here. So you all have several, I guess, natural lakes, man-made lakes too? Mm-hmm. Okay. In Texas, most of ours are man-made. Okay. We have very few natural lakes that are occurring here. Right, and if you look at the United States of America, there are 18 major river basins, and this gives the location of where those major ones are. Do you know what your major river basin is?
I believe it should be the Delaware River.
Delaware River?
Yeah,
okay.
Well, everything here flows to that.
Okay.
Yeah, so that's a pretty large.
Chesapeake Bay's not a river basin?
Yeah, but it's for the Susquehanna. That would be the Susquehanna Basin. And we're right next, we're the next.
It's got us in the same color.
Yeah.
Same color?
Chesapeake Bay and Delaware are in the same.
Right, but they're independent. I'm pretty sure.
I'm just looking at we're all the same.
Well, it just says sources of surface water.
Yeah, and the 18 major ones, so it may not, I'm not sure, I didn't do that research there, so I don't know if one's a major, one's a minor.
I live here, I'm not even sure, so.
Well, yeah.
That's the reason only one is showing up in that area, so which one are they saying is the major is the question, I'm not sure.
It's hard to say.
Well, the Hudson River is up there, there's lots of big rivers, so.
Yeah.
I mean, it's a lot.
Let's see, what number was it? And I can tell you exactly which one it was.
Which number was what?
That you all found yourselves.
17.
It is actually the Mid-Atlantic Basin.
Okay. Well, oh, I see what that, yeah. I'm a little smaller than that, yeah.
Okay.
The Brandywine to the Delaware's in the Mid-Atlantic Basin,
Okay,
I
that's
guess.
where.
Like Susquehanna or probably the Hudson, I guess, is what, some other, the Schuylkill, for Philadelphia.
Yeah, everything around us is in that basin.
Okay, so that's why it's one of the major
yeah,
ones.
okay.
And it's going to be based on size, so think real big outside of our little scope
Yeah,
of the neighborhood.
There you go. So
Yeah.
everything, see, we're 17.
Mm-hmm.
Everything runs into that. Okay.
The Delaware, Chesapeake, everything's in
New
there.
York's in there.
New York's in there also?
New Jersey,
All the way down to, what's that, Virginia? Down to the bottom of Virginia?
Yep.
You got South Carolina or stuff.
North Carolina.
Or North Carolina.
So quite a few.
Yeah.
Yeah, it's big.
Yeah, it's big, it's
It's
big.
big. Number 10, look at number 10.
What's number 10?
Missouri River Basin.
Missouri
Whoa.
River.
That's a big name.
That's huge.
Well, there's a bunch of major rivers up there.
Very
Yeah.
Okay.
Yeah, nice to know information.
Yeah, sure.
There's more than 8,100 major dams, reservoirs with tremendous amount of water in these areas here. When you look at that 1 acre foot, and that's 1 acre, 1 foot deep, can hold 325,851 gallons of water. That's a heck of a lot of water. Yeah, how do we come up with that number?
With that,
Yeah.
1 acre a foot deep.
Okay.
What do you mean?
super.
How
And when
many
you look at the
cubic feet
square
per-
feet of a
yeah.
mile, or of an acre, you're looking at the 43,560, right? 1 foot deep, that gives you cubic feet. And so
Right,
that's
I
how
see.
you get that number 43,560
Oh, okay.
times the 7.48. Roughly, you'll get about that number.
So what, 320 million?
So it's 318.
All right, because surface water is open to so many potential contaminants, a whole lot more contaminants in groundwater. Groundwater is usually filtered, so a lot of the organic material is filtered out prior to reaching the aquifer. But surface water, we don't have that sort of filtration, and so you have a lot of more possible contaminants from the air, from runoff. What are some other things you can think of that will probably contaminate surface
Birds.
water? Huh?
Birds,
Birds, absolutely.
all kinds of.
And do the fish jump out and then jump back in when they do their business? No, they don't. Everything.
Fish are you doing that? Fish don't jump out.
Yeah, exactly. So you have all kinds of decaying organisms that are there that
Leaves,
dies, leave. Absolutely. So it's a lot of
Bodies.
bodies, hopefully
Occasional
not.
Wow.
Hopefully not bodies.
I'm on
but-
tape, aren't I?
Yes,
Yeah,
yes,
okay.
you
I
are.
was just
But a
kidding.
true story concerning bodies.
Oh,
And this was in Baytown, Texas. They cleaned their forebay out, and it had been a while, about 10 plus years. And they found 4 bodies and 3 heads.
The,
I don't know what
besides
happened.
the body, or connected to the body, what do you mean?
No, there was 1 head they did not find.
They didn't find them.
They didn't find the head. They found a body, but not a head. And they were all in a vehicle. So this water had been moving through their plants for how many
The
years?
whole car was in there. They drove the
Yeah.
car and everybody died.
Mhm.
And one was missing a head.
Yeah, interesting fact. So it is true that you could find possible.
So what, do they drive around with a headless body?
I'm not sure. Maybe
Well,
it was
I just,
Frank.
roll off and.
Oh, yeah, that's just roll.
Or maybe it was Frank.
Yeah, it was Frank, there you go.
Frank, there you go.
So common
There he is.
Use your
contaminants.
imagination, Shane,
There you
please.
go.
Well,
Common
we've had dead
contaminants.
deer and stuff like that.
Absolutely.
You know, and dogs even, found, that's what Frankie said, I've never seen those, but
So Frank did find a few dogs.
he's found a dog or 2 over the years and, dead geese actually, dead things,
Yeah. So you can imagine some of the contaminants that we can come across with
Sure.
surface water. Common contaminants will be bacteria, algae, chemicals, sources, again, where you are, a wastewater treatment plant discharge into the waters of the state, which ends up being areas where we're pulling for our drinking water. Downstream, you dump it upstream, I pull it downstream from my drinking water. So when you do your job the way you're supposed to do as far as cleaning up that effluent, it protects me. By your disinfection, it protects me.
Our source water comes right through the mushroom farms up in PA. Lake Creek is where we draw from.
Yeah.
Is it? It's PA, right? Yeah, where they.
Most of our watershed is in Pennsylvania.
They got a big mushroom farming area up there.
But there's been a lot of changes. I mean, they do have like an earthen dike around it now.
It used to be a lot more open, wasn't it? Like
Oh, yeah.
runoff and everything went right from the farms into the.
Right. So there's a lot of improvements, something like that. We don't have many. There's no sewer. There's no.
That goes through Delaware Bay.
Upstream from us.
Downstream
somewhere. It's
from-
mostly the agriculture.
Agriculture runoff.
Or but mushroom stuff is even the.
That all falls under agricultural, right?
Right. But
Mhm.
it's
It's minimal. It's been minimal. It's a lot less than it was.
yes.
It used to be a lot
That's
less.
correct.
All right, so sewage plant effluent, septic tank drainage field, and as you all were pointing out, agricultural runoff, and of course with that, you're gonna have all the pesticides, herbicides, fertilizers that are used in order to enhance our crop, keep the pests away, that ends up in our drinking water sources also. So what do we do to control these sources of contamination? You want to make sure that you're out there inspecting that watershed on a regular basis. We try to control erosion to reduce the river silt, control the algae as much as possible. And what's the #1 way of controlling the algae?
Overdose to copper sulfate.
Copper sulfate.
Did you see the piece of pipe they have from the? I'm sorry, I don't mean to say it, but we were talking about it a little while ago.
Right.
The copper sulfate was eating our aluminum circulation pipe. They have a piece of it over there. They had to take out, they had to replace the
That's
other
what
day.
they did the other day,
Yeah,
yeah.
it looks like Swiss cheese.
We need to get a picture of that.
It's sitting right here. It's about a 4-foot section of the
okay.
aluminum pipe from up there.
So what is a proper dosage, since we're talking about overdosing?
It
What's
was,
a proper dosage?
0.1 to
Yes, 0.5.
0.5 milligrams per liter.
Okay.
And again, we keep it low because it is very toxic. One of the things that you probably should do also is read the SDS safety data sheet. And
Yeah, there's some handouts from the EPA too that
that's for rookies.
make suggestions for different types of algae, what kind of dosages are effective
okay,
and stuff,
excellent.
which we've
Excellent.
used.
So you have some sort of guidelines. SDS are for rookies. Those
Yes.
rookies keep their hands and keep their lung capacity because they are reading it.
We have Bill. He says, a
Okay.
little bit more.
Yeah, wait.
All right. So
Jeremy's
algae
doing it now,
control.
Frank's going.
Yeah.
You may need to pinch the reservoir as well as mark the treatment
Yeah.
plant intakes with buoys. And one of the things that you want to do, and again, it's the rule, it's the law. Not only are we going to mark them, but we're going to restrict any type of activities within so many feet of that intake. All right, as far as regulation of surface water, shoreline installation must have sewage disposal. Disposal should not be within 75 feet of that intake. Disposal not within a 50-year flood elevation. And on your intakes, they should have screens in place. And again, you're going to have to manually or mechanically clean those periodically, regularly. And all activities should be restricted within 200 feet of that intake.
No more fishing down in the plant.
Mm-hmm.
Yeah.
Ours is underneath the reservoir.
What's that?
Reservoir area takes.
But your reservoirs are restricted. I mean, they don't go fishing or boating.
Well, I'm not letting the fishing there, no.
No.
They're not fenced
Yeah,
or
okay.
it's not fenced, it's. I don't know,
Well.
it's not that, but, yeah. But not allowed to, no, not allowed to boat or,
Okay.
we're the only one that takes a boat in there. Actually, supposedly, yeah, as far as we know.
Yeah. All right, lake water is generally low in bacteria and organic matter, while river water can be high in those contaminants. And when we look at surface water as a whole, you're looking at low in minerals, gases, dissolved solids, but very high in turbidity or algae. Those are common problems with surface water. The objectives of treatment, of course, ultimately, first and foremost, is protection of human health. That is what we're striving to do. But in conjunction with that, we want to also supply a product that is aesthetically pleasing. I mean, you wouldn't want to drink water that's yellow and that has all kinds of floating, and you don't know what it is, even though, you know, if you do the test, it may be good to drink.
Safe groundwater is no.
Yes, safe groundwater. It's hard to sell that.
Exactly.
We want to make sure that we're fostering a sense of confidence in our consumer. How do we do that? Make sure, again, aesthetically speaking, the water looks good. And it's kind of hard because you got all these bottled water products out there, and they're like, okay, this is our bottled water, this is our public drinking water. And when they don't match up and look the same, then again, the confidence of our consumers can take a dive there. They can think that it's unsafe, although it may meet those requirements. So we want to make sure we're protecting the health while supplying an aesthetically pleasing product, low in color, odor, but you want to drink water that smells like rotten eggs.
Drinking water systems are more regulated than bottled water.
Absolutely it is.
Aren't they the companies that make the bottled water?
Absolutely. Absolutely. We want to provide quality water to our consumer. We want our product to protect the consumer property. In other words, not a lot of iron or manganese. Now they're stuck with orange, red, brown clothing, or black. So again, why are you looking at Bill on there? Y'all had that incident too?
No, the pink water.
Oh, the pink?
I was like, I didn't know if he was looking, I was looking to see people.
Right, I was
Yeah.
thinking it though, they were passively connected here.
So some of the properties of quality water would be a product that is absent of harmful chemicals, absence of disease-causing organisms, and has very low colorability or solids, little odor or taste, and that it should be non-corrosive and non-staining. This is the goal that we strive to meet every day we come to work. All right, so with surface water, we've already established groundwater disinfection is the required treatment. With surface water, because of the numerous and various different types of contaminants that are present, there are several required techniques of treatment. Aeration would be one, screening, chemical oxidation, coagulation, flocculation. Aeration mostly will do what?
Raises pH.
Aeration.
Brings pH up somewhere. Ours doesn't it?
Yeah, and for our groundwater, the surface water.
We're talking about surface, yeah, I don't think about the other plant. It's been a long day.
That little aerosol can that you spray in the restroom, how are you spraying that?
Under pressure.
It's under pressure and you're spraying it to get rid of odors or gases.
Right.
So aeration is good for driving off gases. Very good for hydrogen sulfide, things like that.
Yeah,
Adding
actually-
oxygen to the water.
Well,
So, very good. Why do we screen them? Why do we have screens on those intakes?
we don't want to
Keep stuff out.
keep pouring stuff out.
Right, because you want to protect your equipment, your pumps and so
Pumps
forth.
and-
Absolutely. You don't want a cow, I don't know if y'all have any cows here, getting in that reservoir haphazardly. And there's no screen in place, and now you really have chopped beef.
Yeah.
Chemical oxidation, here it may be necessary to add chemicals to enhance the treatment process. In other words, we may have lots of fine colloidal type particles, very light, difficult to settle. You add another chemical, give it weight now, flock forms, settle out. We also add chemicals to work with problems such as hard water, to soften the water. So chemical oxidation is a big part of the treatment. Coagulation, of course, is a process of adding those chemicals for particles to clot together and form flock, and then sedimentation. So we have aeration, screening, chemical oxidation, coagulation, flocculation. Sedimentation is where we're going to provide an area quiet, heavier solids settle out by gravity, and after sedimentation, filtration. And finally, disinfection. Ultimately, this will be one of the last steps to ensure that we've adequately removed those harmful pathogenic organisms that are susceptible to chlorine or disinfection. Yes, sir.
I guess the groundwater is different with the, when our aerator went out at Southwell, the pH dropped, but the only thing that changed was the aerator went out. The blower motor, when it kicked the bucket, the pH dropped way down. We had to feed a whole lot more lime to produce the same pH.
Well, that was because, the groundwater that we get is very high in carbon dioxide. It doesn't
So
look
you're
like
sure
soda, like your soda here,
So you're just by removing the carbon dioxide with the air, it's lower.
Yeah, it comes out of solution
Yeah,
easy.
because carbon dioxide is an acid.
Yeah.
Right, but it
acid.
also is doing, like you had said, that the removal of the CO2 gas and replacing it with air, or, oxygen, I guess, or
That
air.
brings the pH.
Right.
The removal is not necessarily aeration, it's the removal of those toxins brings the pH.
Yeah, you could say, either way. But it does, but anyway, what it does is the CO2 is removed to water. It's like 80, 90 parts per million or something like that. But it's not enough to cause, effervescence like a soda.
Right,
But
right.
if you check the pH of this, it's like
It's
4.
low, absolutely.
Oh, it's over 3. It's low. That's why your
You
teeth
feel it
fall
when you
out.
drink it.
Oh, so that's why our teeth are falling out.
Wow.
And that coffee, you can turn it back around.
Exactly,
That
yeah.
coffee, you're looking at a pH around 5 or so.
Okay.
Yeah.
All right.
So,
Right.
yeah, but the carbon dioxide can produce a carbonic acid, which again, any type of acid that's on that lower scale of the pH.
And that's why we had to add more on. So
Nah.
that's why I really want to get that back in service.
Yeah. That wasn't long, I just remember when it went out, that
Yeah,
pH
yeah.
plummeted.
Okay.
Okay.
So, additionally, we're going to pre-treat. Part of the pre-treatment may be taste and odor control, because keep in mind, aesthetically pleasing. Coagulation, sedimentation, filtration, and covered storage, and terminal disinfection. So, all of those are required treatment process. Now, with pre-treatment, we may do something as simple as lake destratification, because when you have the various seasons, you have warm water, you have cold water, and when you have those stratified lakes, you can produce things like taste and odor issue, hydrogen sulfide. And so what's the best way to get rid of those gases? We were just talking about it, aerate, add oxygen. That kind of mixes the lake up, destratified. Other pretreatment process would be control of algae, chemical control, and we'll look at what chemical is recommended, debris removal, pre-sedimentation. Chemical oxidation, activated carbon absorption, all of those could be part of the pretreatment process that we'll look at a little more depth here. So in a nutshell, what we're looking at is getting the water, capturing it from the reservoir via pumping equipment, adding a little oxygen or aerating it, water to remove gases and things like that, then adding chemicals to form the flock, to clock together negative turbidity particles with the positive chemicals that you're adding. Opposite attract, now we have flock. You allow it to settle in your settling basin and then provide some type of filtration, rapid sand filter or membrane filtration. Again, we're going to disinfect it. Now it's ready to go to our consumer. So let's look at the pre-treatment processes in detail. We listed them earlier. We're going to now look at each individually. Reservoir destratification, we said, can get rid of problems such as algae, iron, manganese, as well as hydrogen sulfide. Again, when you have the trap layers of cold and hot, you're going to have these issues. So you can inject air at the bottom from spring to fall to help turn that over, to mix it up, to get rid of those issues. Chemical control of algae can produce taste and odor problems. Algae die, the decaying organic matter will create all kinds of havoc with taste and odor. So it can also chemically and biologically change the quality of the water. So we want to make sure that we're able to do something to rectify, to mitigate this. And one of the ways of doing it is applying an approved algaecide, because this is drinking water. Copper sulfate is one that can be used. And again, we're using small dosages because, again, it is toxic. So you're looking at 0.1. I'm not looking at him. 0.1 to 0.5 milligrams per liter. Debris removal is another pretreatment process, and that can be as simple as providing screening at your raw intake. Now, if you provide screening, you want to make sure that someone is actually out there cleaning it manually or mechanically, because it can get clogged, depending on the size of the stuff you have coming through. Okay, another pretreatment process would be just something as simple as pre-sedimentation. Having a basin or something like that where things can settle out prior to introducing the water to your facilities. It's very effective in reducing turbidity. Another process would be chemical treatment. Here we're going to use meters and pumps in order to meter the chemicals in. Chemicals can be fed in dry or in solution. Now the temperature will affect the chemical reaction. The dosage will affect the chemical reaction. In other words, if I put a whole lot of chemical in, I'm going to get a fast reaction. If I put a weaker chemical in that's not as potent, the reaction takes longer. Activities increase in warmer waters. Cold waters, you're going to get a slower reaction time there. So some of the chemicals are listed that we use in chemical treatment. Can you think of any of them that you use? Alum, I know, is one that we use. What's another one? Polymers, very good. And I think I heard you say something that raised the pH earlier. Lime, soda ash, polyphosphate. There are a lot of ferric chloride.
Ferric chloride, yes.
A lot of chemicals that we use on the water side in order to enhance our treatment process. Coagulation and flocculation. Now, what is coagulation and flocculation?
Making the dirt stick together.
Making the dirt stick together.
In a
Never
very
heard that
basic, easy to understand.
Okay.
Yeah, basically clump it all together so it's easier for the filters to remove.
Okay.
There it is.
So, it does remove materials from water, and as you said, there are some particles that are so fine, they just like to kind of hang out. Not significant way for them to settle out or clot together the way we would like for that to occur. So, how do we do that? You add a chemical in order for the clotting to occur. And again, if you're working with two different charges, that's the principle we're working on, positive and negative charge. We have negatively charged turbidity particles and a positively charged chemical that you're adding. So attraction occurs, and now they clot together to form floc. And then we're going to send it on to have remove it. It is commonly used for your surface water plants. Chemicals are mixed in a rapid mix zone. And then the floc form, it passes on to the next tank. We have the larger floc that settles out. Now, earlier we were talking about jar tests. This is one area where we can utilize those jar tests in order to get a great idea of the amount of chemicals to use, to be efficient at what we're doing, to get the type of floc we want to form and the clarity that we were shooting for. So this is one of the single most important steps, is this process of coagulation and flocculation. Proper mix is required to achieve good settling. Colloidal particles will not settle without correct coagulant dosage and proper mixing. So again, coagulation is both physical as well as a chemical reaction that's occurring. You gotta have the mixing. And you should, when you're setting up your jar test, try to simulate whatever is going on at your plant as far as the speed and all. Different types of mixers that are out there, mechanical agitators, gravity in baffle basins, as well as diffused air mixers, static inline mixers. We have propeller, impellers, horizontal, vertical, as well as bubble size. When we talk about the bubble size and the cost here, again, there's different, I guess, theories out there as to what is more conducive for the process to work. And then pipe non-moving. All right, coagulation, as you told me, process where a chemical reacts with a natural alkalinity in solution to form an insoluble flocculant precipitate. Correct balance is necessary, so the jar test is excellent for the dosage amount. The other thing that we need to be concerned with is the proper mixing, simulate the plant, as well as the detention time for proper settling to occur. And in most clarifier, we want to make sure that we are allowing that flock to settle how long? At least
6 hours.
6 hours.
As long as
Very good.
possible.
All right, the jar test is a required process control. So after it's coagulated, flocculation follows the rapid mix, gently stirring of the flock. In other words, we're going to slow those paddles down for the flock to properly form. And it forms an insoluble precipitate of aluminum or iron hydroxide, that is if you've used alum. Some of the things that will affect coagulation would be pH, temperature, salts, turbidity, particle charge, coagulant dosage, time, agitation or mixing, and the quality of the raw water. In other words, the process of the chemicals binding together is pH dependent. Some chemicals work best at a low pH, others a little higher. So again, you need to make sure you know based on the chemical that you're adding what is the optimum range for the process to occur. We've already said activity is increased in warmer water than cold water. Cold water is very dense. Turbidity is an issue, and that's the amount of suspended particles that are present, as well as the particle charges. Common coagulants that are used is aluminum sulfate, which is commonly known as alum. We have the ferrous sulfates, or the coppers, the ferric sulfate, sodium aluminate, and cationic polymers can be used also. And then there are also coagulant aids that are typically used. Aluminum sulfate is one of the most common ones, and again, pH dependent. Optimum range for this one is 6.8 to 7.5. It requires approximately 0.45 milligrams per liter alkalinity per milligram per liter. Use fiberglass, rubber, or plastic lined tanks and pipes. With the ferrous sulfates or the copperas, optimum range just changed and went up. Very, very, very alkaline, 8.5 to 11. And again, you also can associate this one with softening. Why? Because of the elevated pH. When you usually soften, you do it with lime. Then releases the calcium. Chlorine or lime must be used to get a significant reaction to form the flock. With your ferric sulfate, the trade name is the ferric flock or the ferrosol. Chlorinated ferrous sulfate is also one of the common coagulants that can be used. But notice what just happened. Now, it works best in an acidic environment, 3.5 to 5.5, or alkaline if it's above 9. So pH is very, very important based on the chemical that you're going to use to coagulate your turbidity particles. Here, the required alkalinity of 0.76 milligrams per liter milligrams per liter fed is necessary. The flock form is a little heavier than the alum flock here. We have the chlorides, ferric chlorides, very corrosive. It operates in a wide pH range, highly soluble in water, It needs a little more alkalinity, 0.93 milligrams per liter. So you weigh all of the pluses as well as the cons in determining which chemical will work better for your application. We have sodium aluminate. This can be used to remove fine turbidity and color in low pH, low hardness water. And then after you finish looking at all the coagulants that are there, you have your aids, coagulant aids, activated silica, oxidants, absorbents, as well as polymers to enhance the process. Now, how much do we use? We determine that by what?
The bucket test.
The jar test. Absolutely. Jar testing is a proper process control. It determines the starting point for the coagulant, and it helps the operator to refine the process. Dosing solution, 1 gram of dry chemical added to a liter of distilled water makes a stock solution, so 1 milliliter added to 1 liter gives you a 1 milligram per liter. Okay. And that's just makes things a whole lot easier. Yes. Well, you don't have to go, where's my calculator, where's the formula, what's the specific gravity and all of that, what's the percent purity. So get your right dose. And again, you're going to set up a series of jars. I was about to say or beakers or buckets, because some people will refer to them as beakers.
Yeah,
too.
the square ones are preferred, the cubic shape or whatever.
Yeah.
And so the round ones, I found that I won't.
So we're going to set up different ones, and we're going to add different amount of chemicals in each one in order to see what the final outcome will be. Again, we're seeing how the flock form, what it looks like, the clarity, because we can overdose and end up with a situation that's similar to that. Okay,
No.
waste of chemicals. So jar testing helps us to determine chemical application. We can adjust pHs. Again, the use of lime, soda ash helps us to raise the pH when it's below what it needs. Also enhances coagulation and flocculation. So the next required treatment would be sedimentation. So we formed our flock. What do we do to it next? Send it to a place where separation can occur, settling out. Water flows to the basin, settles out. However, there are factors that will affect that. Detention time would be one. If I were to put a teaspoon of dirt in my water bottle and shake it up and drink it just like that, then that dirt will be all through that water, right? If I were to shake it up and sit it down and let it settle for a minute, what do you think you'll start to see?
It should start to clear a little bit.
Yeah, and where is it clear usually?
At the top.
At the top. If I let it sit there, let's say 5 minutes longer, will I have a greater amount of supernatant or top that's clear?
You should, yes.
Yeah. If I let it sit there an hour or so, will it pretty much settle all the way to the bottom?
You should, yes.
So that tells us the longer the detention time, the greater the settability. And same concept here. If we just put it in and just use it right away, very little settling occurs. Now where are all those particles going? In my stomach in that case, but at the plant, we're talking
But into the water system. I thought we were talking about you were saying drink it.
Yeah, I know.
Oh. You said we shook it up and drank
Oh,
it.
anyway, yeah, but
I know, yeah.
The concept.
Into the system.
Yeah.
Into the system.
there
There you go.
we go. Wake up.
Well, she was
Which
saying
now,
drink it.
I'm going to have to probably increase my backwashing because my filters will catch all that stuff.
Correct, yeah,
Yeah.
yeah.
So, That's the concept.
Gotcha.
All right, there are also factors that influence settling time. What are some of the factors that you think can influence settling?
Temperature.
Temperature, excellent.
Gravity, well, the
Type of flock, right?
size of it.
Size of the flock, the weight
Size
of the flock, very good, very good. What else?
Elevation, depending where you're at, the different elevations can affect this gravity, can it?
Okay, that's a new one on me. I don't know.
Seems like the higher, yeah, okay, maybe I'm reaching there.
That one I don't know, that's a new one on me.
Yeah, some real high elevation places seems like it seems to affect everything else when you get a real high elevation.
That's true.
Yeah.
And in Texas, we don't have too much elevation.
No, that's right.
Pretty much all flat. We're pretty flat
That's a
here.
good one. I'll have to look into that one
Yeah.
because I don't know that one. If that does. Okay. The velocity. Velocity through the tank will affect the settling. If something is moving real fast, it's not going to settle out. But if we slow it down, it's enough time to settle out. Then we need to remove the sludge periodically. Then we're going to look at settling tank zones in a minute here. So, as you told me, particle size, shape, specific gravity, all of that will affect the settling. Type of turbidity. Again, the particle, whether it's colloidal, charges on that turbidity will also affect the settling. The temperature of the water, detention time, said that in short circuiting. What is short circuiting?
If you charge, there's positive and negative charges.
Okay, think of flow, but short circuiting, because it's a flow issue. It's when you have uneven flows through the basin. Okay? And what that does, it decreases the detention time. And with the decreased detention time, go back to the bottle with the soil.
You're keeping it stirred up if you don't have even or,
Right.
This is an advantage of your
Absolutely.
all the air that you've got.
So that's what when we talk short circuiting, it's the uneven flow through that
It's like the
basin.
water, if you're bringing the water in,
Bypassing, yeah.
if it's hitting the wall or something where it's coming into the basin, instead of just flowing smooth, hitting the wall and going all over, or however it might, That's the idea of it, right?
Yes. And then another thing that can affect the settling, we had a poor design, poor construction of the basin to start with can hamper the settling process.
Kind of goes hand in hand with short circuiting things, doesn't it?
Absolutely, because a lot of times you got to get out there, maybe add baffles, make sure your weirs are properly arranged in order to make sure that that flow is going the way it should.
A good example, Shane, is that raw water tank at South Wellfield. There's baffles in there. And the reason there are is that it kind of forces the water to go around the tank. See, if there weren't any baffles, it would just go in, that the water in the back of the tank would just stay there. Wouldn't circulate. So they did, want to design, right, so it has to go this way to get back over to the intake for those pumps. So
Contact.
Excellent example.
The front tank's not like that, is it? It's
No.
not baffled.
no, it isn't. Could be, but
That's just pretty, that's high velocity though in that tank.
Again, you can have different basin design. We saw rectangular basin, which are very, very, very typical for water plants. We also have the circular basins also. Okay. Center fed with the circular one, circular peripheral fed, or square center fed. All right, we talked about detention time. Detention time is just that amount of time that the water resides in a particular basin or flows through that basin or is retained in the basin. And so for our sedimentation basin, a minimum of 6 hours is what we're looking at as far as a requirement. Another slide talked about the settling zone there. Now, with the settling zones, we have an inflow coming into the plant, which is considered the sedimentation basin inlet zone. Then you have a zone with settling occur, where again, the flow is equally distributed over that particular basin. Particles are heavy enough, will settle out. And that's your settling zone. Then heavier solids will fall to the bottom, creating your sludge zone. And what happens if I just continuously let that sludge build up and up and up and up and up without getting rid of it or taking it out and up? What's going to happen?
Costs you a lot more to get rid of it when you finally decide to do it.
Oh, yeah.
Well, before I get to that point, I'll start, it probably will see taste and odor issue. There'll be a rediluting of that sludge.
You're just concentrating all the contaminants that you're removing, that you're settling out, you're concentrating more and more and more, and if you're using the same basin.
Yeah, and you got to make sure you have a routine schedule to remove the sludge from the bottom of the sedimentation, because it can lead to taste and odor issue, all again, as well as the quality of the water. Now, did that door just open by itself?
It sure did.
Hi, Frank, come in and join us. See, Frank has really been trying to get in here all day.
Yeah, everybody's laughing at me earlier, but imagine 3 a.m. in here by yourself when stuff like that happens. It's creepy. I'm telling you, everybody's laughing at me in the day.
It's creepy just when it happened just with us.
Yeah.
Okay.
He gets nervous.
I'm glad that it's just showing that he approves of what's going on. And he's so proud of you for sitting in class and getting this training.
Yeah.
Because he was
I didn't know it at all. You've obviously never even met him.
Okay. So we have the inlet, the outlet zone in is where I clarified liquid will flow from. Okay. So those are our zones of our settling tank. All right, what time do we have?
It's a little after 2.
All right, let's take a